So we're not going to go into a lot of detail on any of these particular batteries, but talk a little bit about some of the half reactions that take place in some more popular batteries that you come across basically every day. Car batteries, your alkaline batteries, which are the AAA, AA, C and D, 9 volt. Cell phone batteries, those are lithium ion typically. And then a couple of terms that you should be aware of. A primary cell, which is a battery that can't be recharged, and a secondary cell, which is a rechargeable battery. Just some nomenclature from the battery world for you. So your car battery is a type of lead acid battery. There are 6 voltaic cells in one single car battery, and each of those voltaic cells produces 2 volts. So if you link them all together, you end up with a 12 volt battery. At the anode in the lead acid battery, you have solid lead. And in fact, the oxidation reaction is lead solid plus HSO4 minus, so it's sulfuric acid, 1 deprotonation. And that forms lead PbSO4, and that's a solid, plus H plus 2 electrons. Okay, so that's your oxidation reaction. And then at the cathode, you actually have another solid. It's lead oxide, and in this reaction, you'll have PbO2, so that's your lead oxide solid, plus HSO4, aqueous plus 3H plus 2 electrons, forming PbSO4, lead sulfate, plus 2 water. So if you take your oxidation reaction and your reduction reaction and add them together, you end up with the equation that's written on the bottom, and that's the overall cell reaction for the lead acid battery. I wanted to find a video on YouTube of someone pulling apart a car battery, so I went into the YouTube rabbit hole of finding stupid videos. There was a video of, you can find videos of people taking apart car batteries, but they're doing things really stupidly. For instance, pouring the sulfuric acid out of the battery without wearing goggles inside. And then they start saying really incorrect chemistry, so I didn't want to show a video of it. But if you want to know what the insides of a car battery look like, you can look it up. I don't recommend pulling them apart yourself. Alright, so then your alkaline batteries, these are kind of an interesting build. So the whole thing, of course, is in a case, but one of the casings, let me see here. Okay, so this, the darker gray area that I'm drawing on here, this is the manganese oxide. It's the cathode. So the cathode actually goes around the entire outer part of the battery, and the anode is in here. So I should erase that for sure. There is a rod that goes through the middle of the battery that connects to the negative terminal. The positive terminal is all along the outer edge of the battery itself. And there's just a really thin film, porous paper, that's this line, that separates the anode from the cathode. And that basically acts as your salt bridge. So even though the design of the alkaline battery looks very different than your typical, the figures we've been showing for voltaic and galvanic cells, it's essentially the same thing. It's just a different arrangement of the components. So in this battery, there is zinc metal that's sort of dispersed in a gel, and the cathode, so that's the anode. The cathode is the manganese dioxide with some graphite, and it's all suspended in potassium hydroxide. So if you ever see an alkaline battery that has the crust on the outside, it's basically broken and leaking, it's not actually leaking battery acid, it's leaking a base. It's that potassium hydroxide. So for half reactions at the cathode, so our reduction, we'll have 2 MnO2 solid plus 2 water plus 2 electrons forming 2 MnOH. So this is a interesting base form of manganese oxide, and that's a solid plus 2 OH minus. So just real quick here, the lead acid battery, you notice there's a lot of H plus running around. Here we have OH minus. This is the reason why we had you balance redox reactions in both acid and then learn how to do it in base. Because you need it for these, to be able to actually balance these if you were to do so. At the anode, we're going to have our zinc solid plus 2 hydroxide forming zinc hydroxide, which is a solid, and then our 2 electrons. And so you could add these up, electrons are balanced, and figure out the overall cell reaction. Okay, no pictures on this page, sorry. Here we're going to look at a couple of rechargeable batteries, NiCad, nickel cadmium batteries, and nickel metal hydride. So these are sort of competing in the market, I guess, in terms of your rechargeable batteries. I have a colleague who once asked another colleague who was an electrochemist which rechargeable batteries she should buy, NiCad or nickel metal hydride, and the electrochemist said, well, at least the NiCad won't explode in your face. So my important tidbit here for nickel metal hydride is that it could explode in your face. Not necessarily that important to know, I suppose, but that will not be on the exam. In the NiCad battery, okay, cathode nickel, it's a hydrated nickel oxide. We can write these equations out, or you can just look them up. I'm not feeling it today. Also probably won't be on your exam. So the other kind of interesting thing is, so I mentioned before how when you recharge a battery, or you're plugging your phone to recharge it, essentially what you're doing is you're reversing the half reaction. That's true here. So when you charge or recharge a battery, the half reactions are reversed. So you're basically forcing a non-spontaneous reaction, the reverse reaction, to go. That's why you're plugging in a device to make that reaction go in the reverse direction. And then the spontaneous process is the discharge from the battery itself. The battery actually operating as a battery. Okay. questions on any of this? All right. Couple more things here. Lithium-ion batteries. These are kind of neat. This is what powers a pacemaker. Lithium-ion batteries are lightweight. They're small. They have what's called a high specific energy density. So that a specific energy density is the amount of energy stored per mass. So a lot of energy in a small amount of mass. Similar term, they have a high volumetric energy density, so that's the amount of energy stored per unit of volume. I have an electric toothbrush, one of those Sonicare toothbrushes. I think I've had it for almost 10 years now, and just to be clear, I do change the heads appropriately. But I can tell that it has a lithium-ion battery. I can tell that I have to plug it in a lot more and recharge it a lot more frequently now. It's almost every couple weeks, whereas at the beginning it lasted for a much longer time. But yeah, so this is what's used in a pacemaker. It's kind of cool too. They can be really small. Okie doke. Okay, hydrogen fuel cells. I think these are really cool. But so what happens is you take a hydrogen gas. You need to have a constant flow of hydrogen gas. It goes into the cell where it diffuses. The hydrogen gas diffuses across the anode, and electrons are generated, and they flow in a particular way, go across the circuit, and then basically flow back in. The electrons are generated in a platinum catalyst. This is platinum. And then those electrons then also will meet up with some oxygen to generate water. So, got everything all mixed up here. When the only thing that's discharged from the exhaust of a hydrogen fuel cell car, 1/2 is water, which is nice. There's no CO2, none of that. And the cell potential is 0.7 volts. So it's not a lot, right? But you do this a lot. You have a lot of cells all linked together. Okay. Let's see. Okay, so again, we have our hydrogen passing through the catalyst, the platinum catalyst, generates 2H plus and 2 electrons. So H2 forms 2H plus 2 electrons. It migrates through where it then meets with oxygen to form O2 plus 4H plus 4 electrons forms 2 water. Okay. One of the other things that people worry about with hydrogen fuel cells is the fact that hydrogen is explosive. And we do have a pretty, I guess, scary example of how hydrogen has exploded and killed a bunch of people with the Hindenburg. But I think that gas is also extremely flammable. Right? So I don't know if that's a really reasonable scare. It might be, but anyway. Does anyone know when the electric car was invented? Yeah. Yeah, it was really, really long time ago. It was like the 1860s, something early on, and then Ford came along and sort of said, yeah. There's also a really great episode of Mr. Rogers' Neighborhood, if you're into that, from the 80s. Remember that episode? It's a memorable one, where he rides in an electric car. It's great. The opportunity to buy a hydrogen fuel cell car, I totally would. By opportunity, I mean cash, and a place to get hydrogen. So really, I have no opportunity right now. Okay, a couple things here. Let's just finish this off and we'll be done. Okay, so electrolysis. Electrolysis is a process where we make a redox reaction happen by supplying energy. So we're going to need some energy source. This picture we're showing a battery being used. In this case, we are generating sodium metal and chlorine gas at 2 electrodes that are dipped into molten sodium chloride. So very high temperatures involved here with this reaction. You got to get that molten sodium chloride. Again, we've got our anode that's connected to the positive terminal of the battery and our cathode that's connected to the negative terminal. So why would we want to do this? Here we're making a non-spontaneous reaction happen. If we needed to generate a large quantity of liquid sodium, we could do that with this, or chlorine gas, we could do that with this. Also, the process of electroplating that essentially occurs in the same way. Forgot to put in the Oscars, the Oscar award. It's actually electroplated. I have a cool picture of that. I wish I had put it in. But the process of electroplating is basically putting a pure metal on the outside of another metal object to make it look pretty, basically. So in this process, in this figure of electroplating, we're going to take some impure copper. Let's say it has copper ion and zinc ion. And we're going to use electrolysis to electroplate pure copper onto a copper cathode. So we do this in a way so that zinc does not migrate to the copper cathode. We end up forming more copper on the outside of our cathode and losing copper from our anode, and we end up with sort of a sludge at the bottom from a leftover stuff that was not copper. I have this on. So you will see some examples. Again, this is not. This is for the next. This is for your final. We're almost to the final. But you will see some examples of this in your homework as well, looking at electrolysis or electroplating. So let's look at an example of when we're electrolyzing sodium chloride, molten sodium chloride. At the cathode, we're going to have this reaction taking place, the sodium ion plus an electron forming liquid sodium. At the anode, we're going to have the chloride ion forming chlorine gas and an electron. So you can see that 1 mole of electrons is transferred or reacting with 1 mole of sodium ion. So the stoichiometry here is going to be important. Okay, same with other types of problems, but this is going to come into play for sure. So, so when 1 mole of electron reacts with sodium ion, 1 Faraday of charge passes through the circuit. Okay, because a Faraday is equal to 96,485 coulombs per mole of electrons. Okay, so if we have 1 mole of electrons from the sodium, that's a Faraday. So here's an example problem. When molten sodium chloride is electrolyzed, sodium is deposited. If a constant current is passed for 5 hours at a current of 6.8 times 10 to the minus 2 amperes, how many grams of sodium is deposited? So these types of problems They sound very confusing initially, I think. But really, all you need to be able to do here, maybe I shouldn't say it that way. You need to be able to do dimensional analysis here. So if you can keep track of your units, you should be able to solve these problems. Another bit of information that you'll want to know is that an ampere is equal to a coulomb second, right? Why do I keep losing everything? There we go. Okay, so I'm going to walk you through this problem, and then I'm going to give you another example and have you guys work on that one yourselves. Okay, so sodium is deposited if constant current is passed for 5 hours. We know we have a length of time, and the current is 6.8 times 10 to the minus 2 amps or coulombs per second. We want to find grams of sodium. Okay, let's start with what we know. Let's start with our current. We'll have 6.8 times 10 to the minus 2 coulombs per second. I haven't done much dimensional analysis with you guys, so this will be fun. So we know we're going to pass current for 5 hours, so we need to turn our seconds into hours. You might know the conversion factor for that, but I'll go stepwise. 60 seconds in 1 minute, 60 minutes in 1 hour, and we're doing this for 5 hours. So from this, we're able to figure out how many coulombs we've used. But that's not what we want. We want to find grams of sodium. So we can use our Faraday constant, 96,485 coulombs per mole of electrons. So coulombs was in the numerator. We're going to put that in the denominator. 96485 coulombs per mole of electron. And we also know from our cathode reaction that we have 1 mole of electrons per 1 mole of sodium. So 1 mole of electrons in the denominator, 1 mole of sodium in the numerator. But we don't want moles of sodium, we want grams of sodium, so we can use our molar mass. It's 22.99 grams of sodium per mole. Okay, so now our coulombs cancel, moles of electrons cancel, moles of sodium cancel, and we're going to be left with grams of sodium. And I believe it's 0.292 grams of sodium. All right. Questions on this? All right. Let the units guide you. Everyone got this? I'm going to switch to the next slide. Okay, here's another good problem. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the current is 10 amperes. So you're going to need a couple of things. Remember what amperes are in terms of coulombs per second. How many electrons are transferred. And keep track of where you're starting and where you're going. I'll let you try this one out. How's it going? I think one of the important things to recognize here is that the aluminum chloride is going to form aluminum 3 plus ion and 3 chloride ion. So then we're going to have aluminum 3 plus 3 electrons forming an aluminum solid. So 3 electrons transferred. Sometimes it's tricky to figure out where to start. We've got 2 options essentially, 1 hour or 10 amperes. Could probably start with 1 hour, but that's not what I would do. So I'm going to start with the way I would do it, which is 10 coulombs per second. It's 10 amps. Again, using my dimensional analysis to be able to figure out how many coulombs in an hour, essentially. 60 minutes, 1 hour, and then we're doing this for 1 hour. Okay, so hours, min, seconds all cancel. Again, we'll use our Faraday constant, 96,485 coulombs per mole of electrons. Three moles of electrons for 1 mole of aluminum. And that's what we just figured out based on the formula. And then you go from moles of aluminum to mass of aluminum. (27 grams per mole). 3.36 grams of aluminum. Questions on that? Super fun. There's one more problem. I'll let you guys work on it, but I'll give you the answer. I think this one's actually from your book. So this brings us